During World War II, two scientists, Max von Laue and James Franck, were trying to hide their hard-earned Nobel Prize, that was a gold medal, from enemy forces. They sent it to a fellow scientist to hide it, and he hid it by dissolving the medal in a chemical called aqua regia. This fellow scientist was Niels Bohr, who became famous for his atomic model known as the Bohr's atomic model. In 1913, a scientist named Niels Bohr introduced certain quantum principles as hypotheses to the Rutherford atom to explain its stability and also the emission of spectral lines at discrete frequencies. Hypothesis 1. Of all the classically possible orbits that an electron can have, the electron can exist only in such orbits where its orbital angular momentum, h upon 2 pi, has value equal to an integral multiple of h upon 2 pi, where h is a universal constant known as Planck's constant. That is, h is equal to 6.625 times 10 raised to the power minus 34 joule seconds. Such orbits are stable orbits, and an electron in a stable orbit does not radiate energy. Hypothesis 2. When an electron makes a transition from a stable orbit with energy EI to a stable orbit with a lower energy EK, the difference of the energy EI minus EK is radiated away as a quantum of electromagnetic energy with a frequency f, such that EI minus EK is equal to HF. Similarly, when an electron in the orbit of energy EK absorbs a quantum of energy HF is equal to EI minus EK, it makes a transition from the orbit of lower energy EK to that of a higher energy EI. Energy of an electron in a hydrogen atom. An electron having mass m moving in a circular orbit around a nucleus. Let v be the linear velocity of this electron in its orbit of radius r. Here z is the atomic number, which is 1 for a hydrogen atom. The centripetal force for the circular motion of the electron, mv square upon r, is provided by the Coulomb force of attraction, 1 upon 4 pi epsilon 0 into ze square upon r square, between the negatively charged electron and the positively charged nucleus. Here, epsilon 0 is the permittivity of free space. Using the first hypothesis of Bohr, the angular momentum of the electron in an orbit is restricted to mvr is equal to nh upon 2 pi, where n is an integer. N is equal to 1, 2, 3, etc. N is called the principal quantum number. Therefore, m square v square r square is equal to n square h square upon 4 pi square. V square can now be eliminated from the equations. Further equating, we obtain an expression for r as r is equal to n square h square epsilon 0 upon pi ze square m. Now, the total energy of the electron in this orbit is En is equal to kinetic energy plus potential energy is equal to 1 by 2 mv square minus ze square upon r into 1 upon 4 pi epsilon 0. Using equation and multiplying 1 by 2 on both sides, we get 1 by 2 mv square is equal to 1 upon 8 pi epsilon 0 into ze square upon r. Substituting this value for half mv square in the equation, we get En is equal to 1 upon 8 pi epsilon 0 into ze square upon r minus ze square upon r into 1 upon 4 pi epsilon 0. Hence, on further deriving, we get En is equal to minus 1 upon 8 pi epsilon 0 into Ze square upon r. Using the value of r from the equation and putting it in the equation, En is equal to minus 1 upon 8 pi epsilon 0 Ze square into pi Ze square m upon n square h square epsilon 0. En is equal to minus z square e raised to the power 4m upon 8 epsilon 0 square n square h square. Z being the atomic number for the atom is equal to 1 for hydrogen. Hence, we get En is equal to minus e raised to the power 4m upon 8 epsilon 0 square h square into 1 upon n square. Note that the energy of an electron given by this is negative. Let's summarize. The electron can exist only in stable orbits where its orbital angular momentum has a value that is equal to an integral multiple of nh upon 2 pi. When an electron makes a transition from a stable orbit with energy Ei to a stable orbit with a lower energy Ek, the difference of the energy Ei minus Ek is equal to Hf. According to Bohr's model of an atom, electrons revolve around the nucleus in certain orbits. What is the other term used to define these orbits? Stay tuned to find